Hello, hello, welcome one, welcome all to another day of daily LeetCode live streaming here with your host, Raphael. I think it's the first time I may have ever said my name, but my name is Raphael, so with your host, Raphael. Today, it's been a pretty awesome Thursday, been a very productive day at work, so I'm really happy to now transition over to the sort of LeetCode live show. It's definitely one of my favorite things to do for the day, one of my highlights. Before we get started, I just want to go over some quick housekeeping. So yesterday, I made a quick change to my website. So now if you're on the website, I realized that you might want to look up things by topic, but a lot of times you find a question on LeetCode, and let's say you want to know if I have actually covered that question before. I mean, I suppose you can do a Control F on the browser, but just to make it a little more intuitive, let's say you want to see, oh, has he done anything related to like binary questions? You can type binary here and I'll show you all the different types of binary questions you've done or I have done. Maybe you want to find questions related to a list. Here you'll be able to find all the questions related to a list. Or maybe, I don't know, like node, is that like a popular word? Tree, anything related to trees. So yeah, just added search functionality. I hope that makes it a little bit easier for everyone to keep track of their progress, makes it a little bit easier for everyone to navigate the site. So would love to hear any questions, comments, concerns you have about that. Would love to hear the feedback. I really hope this has been helping all of you out. We are only 2 questions away from reaching 100 top quality questions on my site, and we have since yesterday officially gone over our 200 question mark, which again is very amazing. I'm very happy to have made it this far. I have never made it this far in my LeetCode journey ever, and I've been doing this for like more than 3 years, so it's definitely a huge achievement for myself. So very cool. I also realized that, have we been, oh, okay, no, we're just on a streak right now. Refresh your streak. It doesn't keep track of like my daily streak. Oh, it's okay. It's fine. Anyway, without further ado, let's get started. We're on page 3. We're going to resume today with majority element. And let's see what this has in store for us. So, given an array nums of size n, return the majority element. The majority element is the element that appears more than n divided by 2 times. You may assume that the majority element always exists in the array. Could you solve the problem in linear time and in O of 1 space? Now, the size of this, what is the size of this? N equals nums.length. Given an array nums of size n, return the majority element. We don't actually know. Okay, this can go all the way up to what? 10 times 10? Okay, 10,000. I mean, we probably could, like, I guess constant space, technically, we could create an array of size. And are these majority element? But I guess this number, oh no, because the number can actually go out of the bounds. So I can't do anything with this. Okay, I feel like there's sort of a trick here, right? Like, the majority element is the element that appears more than n divided by 2 times. Now, I do remember the trick here. It's not an algorithm that really anyone probably should be able to whip up in an interview. It's one of those things that if you've seen it, you can do it. I believe this one's called the Beyer-Moore voting algorithm. Beyer-Moore voting algorithm. Beyer-Moore voting algorithm. Yep, is one of the popular optimal algorithms which is used to find the majority element among the given elements that have more than n divided by 2 occurrences. Exactly, there you go. Yep, VP Pat, you're on it. Yeah, so I think what we can do is, I kind of want to try and solve it both ways. Beyer-Moore is just an algorithm that I've memorized. So it'd be nice if I can attach like other links here. Maybe I can just like share these on the chat, and that will give at least other people watching like the ability to be able to look up these algorithms. So we should probably solve it both ways. Let's go ahead and solve it with the extra space. And really, if you think about it, what is it that we need to do? We just need to keep the frequency of each one of these numbers as we go along. And once we get over n divided by 2, and I'm guessing they want that floored, then we know that's the answer. So we can say, for example, const frequency, right? And now we can say for const n of nums, let's see, we want to add it. We can add it and then check it. So we can say frequency of n equals frequency of n plus 1 or 1 if frequency of n is greater than math.floor of nums.length divided by 2, then we just want to return n, right? And it always exists in the array, so this return here is fine. We don't need to do anything after this for loop here. So let's go ahead and run this. Let's go ahead and run it for all of our different test cases, and let's see what we get. 3 and 2, 3 and 2. Let's go ahead and submit that. Yeah, so it says it runs in 8.51% time. We all know that LeetCode, you know, the difference in the time anytime you click on submit is vastly different. Let's see. 62.69. So yeah, you can see there's a large difference there. I would think that if you can, you know, if you solve it this way, I don't think there's anything wrong with that. You know, I would even go as far in saying if you get this in an interview and you solve it like this and you explain your reasoning behind it, I think that's totally fine. I think knowing the Beyer-Moore algorithm will definitely that'll be like the cherry on top, but I wouldn't think it's necessarily expected of you to know that. So how can we now adapt it to fit this Beyer-Moore algorithm? And let's analyze this, right? Like, what's the time complexity here? I mean, at most, like in here, we have to go through every element to figure out that it was 3, right? So in worst case, it's going to be linear. And then the frequency here will just be as large as all of the unique elements in the array. So that's why it makes it this have some n of space complexity, right? If we want to get O of 1 space, I believe the way it works is, let's say we're going through this, right? we essentially keep track of two different variables here. We keep track of sort of count and the current candidate. Now, what we have to do is the first thing in this array is going to become our candidate. So let's say candidate is 2 and our count will be 1, right? And hopefully that's clear to everyone watching. Like the candidate's 2 because that's just our first thing, and the candidate's 1 because, well, there's only one of them. So imagine we start here in the next one. If it's the same, like any time the number is the same as the candidate, right, we increase count. So now we have 2 of candidate 2. Now we get to 1, it's not the same, so now we have 1 less. Here, count becomes 0 because we have 1 less, right? Now here's where the next piece comes. Anytime this count gets to 0, we also flip our candidate to the thing that made it 0. So our candidate here will be 1, and then we resume. Now count is the same, so we go to 1. Count is, or rather the candidate is different, so now count goes back to 0. We update candidate, we go to 2, count becomes 1, and then essentially we just return the candidate. So if you had asked me to explain it now, like why does that work? Maybe we can also look up why this works. When the elements are the same as the candidate element, votes are incremented when some other element is found not equal to the candidate element. We decrease the count. This actually means that we are decreasing the priority of winning the ability of the selected candidate, since we know that if the candidate is a majority, it occurs more than n divided by 2 times, and the remaining elements are less than n divided by 2. When votes become 0, this actually means that there are the same number of different elements, which should not be the case for the element to be the majority element. That makes sense, somewhat. So I think that, you can certainly read the article that I linked. I keep going on different tabs here. But let's go ahead and try that different solution, right? So I'm going to comment this one out. I'm going to do the same thing I had here. Let's say count is 1, and my candidates is just going to be nums at 0. Now we can have a for loop that goes from 1, nums.length I++. Right, we can say if nums of I is equal to candidate, then we say count plus plus, else count minus minus. If count is equal to 0, then we say the new candidate is equal to nums of I. And down here, we should just be able to return our candidate. So let's go over this now. Let's run this guy. 2, 2. Okay, so it looks like we have a little bit of a bug here. If nums of I is equal to candidate, count plus plus, right? Nums of I is equal to candidate, else count minus minus. Okay, 1. Here, count minus minus is 0. If count equals 0, candidate equals nums of I, which is 1. If nums of I equals candidate, nums of I equals candidate, count plus plus, that's 2. Oh wait, did we never, oh no, 0. So candidate now equals nums of I, which is 1. Come over here. Nums of I 1 is equal to candidate. Yep, because we just changed it, so 1. Then we come here. If nums of I equal to candidate, no. So count minus minus. If count equals to 0, candidate is nums of I. 2, 2. Oh, wait a second. Did we... 2, 2, and 2, 3. Should we not be starting at the first one? Maybe I should make this 0. And then we'll just increase it from there. And instead of starting here, let me see if that actually changes anything. I thought it was okay that we start at 1. Because that would be the same thing, right? Yeah, there isn't really a change there. So what is happening here? 3, 2, 3. We have 1, 3, and then we change to 2. That goes to 0, so the new candidate is now that. Yeah, that should work, no? Count is 0. Candidate is the first one. If nums of I, which is here, is equal to candidate, we increase the count. Count's not equal to 0, now we increase I. If nums of I is equal to candidate, which is not, we decrease count. If count equals 0, then the candidate is equal to 2, okay? Come up here, if nums of I equals candidate. Oh, maybe I should be doing this. Maybe this should be the other way around. Sorry, I think my dog is a little bit sad. He's barking a lot. Let's try out VP-Pat solution here. Let's try to count at 1. 3, 1, 3, 2. No, I think it's something else that's happening here because we just went over it here, right? I think count as 0. Let's go over everything here. If nums of I equals candidate, which we've never done, so I think maybe this can stay as num0. Count plus plus, okay. Is count equals 0? No. Now we go to the next one. If nums of I is 2 equal to 3, remember this is 3. 2 is not equal to 3, so we do count minus minus, which becomes a 0. Count equals 0, so candidate now equals 2. Go to the next one. If 3 is 3 equal to candidate? Yeah, this is the weird spot because maybe I need to like reset. You know what? I wonder if I need to also reset. Yeah, I think I need to reset 1. I think I need to reset count to 1 here. So that way, like right over here, let's just like start this over again. Nums of I equals candidate. Yep, so count plus plus. Cool. We go over here. 2 is not equal to 3, so count minus minus 0. Candidate I equals 2 and count equals 1. Go to the next one. If 3 equals 2, count minus minus 0. Candidate equals 3. Yeah, I think that's what it was there. I think we had to reset the count back to 1. Let's try this out. 3, 2, 3, 2. Let's run this. 44.22. Sweet. Yeah, so this is neat, right? Now we still have the same time complexity. We still have to iterate over everything, but we're not having to necessarily keep track of anything in this store right here. So because of that, we have constant space complexity. So I think it's very worth it for you to understand this algorithm. I think it's one of those that it's almost like Hamming weight or binary search or a lot of these famous algorithms, you just memorize it. I don't think there's really any harm in that because either way, like what's going to happen in an interview, right? A lot of people, their argument is like, oh, if you memorize it and you just do it really quickly, they're going to know that you just like memorized it. Here's what I would do. I would very quickly tell your interview about this solution here, but I probably wouldn't write it out. I would say, oh, I know how to do it with an object literal and a single for loop. I can keep track of the frequencies in here and it'll give me linear time and space complexity. But I also know of a better way and we can solve it using the Boyer-Moore majority voting algorithm. That's what I would do. And at least they know like, well, even if you did memorize it, you took the time to memorize it. So that must mean something, right? That must mean that you're like a decent interviewer or like someone that cares a little bit about this stuff. And that's probably a good thing. So that's my argument. We'd love to hear what you all think, but I think we're good on this one. Phenomenal question. I'll definitely be adding this to my list. I mean, look at this, 11,000 people. That's a lot. That's like probably the second one right after twosome of the best question you can do. That's awesome. So that's our first question we've done, and the first question we'll add to my list. That means we only have one more question to reach 100 on my website. So let's go to the next one. Let me remove this. I'll remove this, and I'll remove this. Let's do find lucky integer in an array. Nice, another high quality question here. Given an array of integers R, a lucky integer is an integer that has a frequency in the array equal to its value. Okay, so I mean, we need to know the frequency of everything first before we scan through it a second time and figure that out. Like 2 has a frequency of 2, so the answer is 2. 3 has a frequency of 3, so the answer is 3, and I'm guessing some will have none. So look at this, check this out. I'm getting, or fumble and pretend like you came up with Boyer-Moore algorithm on the spot. Yeah, okay, does anyone play like Fallout? If anyone plays Fallout, then the suggestion that VP-Pat like said, that's like super high charisma because it's hard to fake it when you actually know it. You actually have to like act it out and pretend that you don't know what you're doing, even though you sort of do. And you have to convince them that you really don't know, even though you do. So that's like super high charisma. So that'd be, yeah, I mean, go for it if you can, for sure. All right, so check this out, right? I knew this was a frequency problem. First thing I think is, okay, keep track of frequency and object literal. But now I've gotten so used to this stuff that I know that constraints are very important. The first thing I did was I looked at my constraints because this will help us make the space complexity constant. We see here that R is length is 500 and the length, the range of numbers in each one is 500. So this means I could create an array of size 501 and I can just use that to store the frequencies. Now I have a constant size array. I don't have to worry about a growing object literal. You know, it might be bigger for some inputs, smaller for some inputs. This will make it so it's always constant. So let's do const frequency equals new array 501. I'm going to fill it up with 0. And what are we going to do here? We're going to go through each one of our different numbers. So we'll say for const n of r, we can just say, actually, we can not even have to do a new line here, really. We can say frequency of n plus or equals 1. All right, so now we have the frequency of where it is. Now we can just go through r again. And if we can say if frequency of n is equal to n, then we return n, else we just return -1. I feel like that's going to be the answer there. So let's run this and see. 2, 1, and -1. Okay, so close. Let's see what happened here. So frequency, new array, 501. So 2, 2, I should have 2 there, 3 and 4, okay. This part should be fine, right? And then we say for const n of r, now we're going to 2. I want to look inside of 2. If the frequency of 2, let's see, is equal to 2, return 2. Okay, that's fine. And then we get to 3. Okay, so actually the first one was right. Let's see what's up with the second one. Why wouldn't this one be right? We add 1, we add 2, and then we add 3. So let's just imagine we have an array that looks like we're going to have 0, 1, 2, and 3. We add 1, then we have 2, and we have 3. For const n of r, so we come through here. All right, if frequency of 1, oh, return the largest of them. Interesting. So that's cool. Yeah, that completely missed that part. Did it even say if there's no lucky integer, return? Okay, so there's actually an easy fix for this. You might be tempted to like create a new data structure and keep track of all the different numbers you viewed and then somehow return the max. But if we just start at the end of this array, if we start at the end of frequency, let's think about this. I can start at the end of frequency, and if the index I'm currently on matches the amount it shows up, then we just return that. I think we can do that. So we can do for let I equals frequency.length minus 1, I greater than or equal to 0, I minus minus. Let's see, if frequency of I is equal to I, then we should return I. I think that will work. 2, 3, ooh, 0. Close. Oh, I know why. This is also considering 0. We shouldn't go all the way to 0. Because 0 will be 0, right? There you go, 2, 3, -1. So let's run this. Okay, so I want to point out 2 things that I realize are very important in these questions that I don't think I would have learned if I didn't do these streams. Okay, so let me go over them again. Let me mute my phone real quick. Apologies if you guys have been hearing vibrations. I have pest control in the house, so my alarm keeps going off anytime it notices someone. Okay, so check this out. What are 2 very important things that we did? So like I said, I could have instead created an object literal like this. But this is dynamic, right? Like we don't know, the compiler, the engine that's looking at this code doesn't know if this is going to be small or large depending on the size of the input. So it can't do any nice optimizations for us under the hood, right? But if we do something like this, This is just a contiguous block of memory that you create once, and it doesn't matter the size of R, this will always be the same. That's where we get the optimization. And I was able to do this because I looked at my constraints. This is one thing that easy questions take advantage of, these nice constraints. Medium and hard questions have different constraints, and we might not always be able to take advantage of things like this. These are very important things to look out for when you're doing questions like this. So that's one thing we did. And now check this out. The second thing, 1, 2, and 3 are all lucky numbers. Return the largest of them. Because I have this array, right, and I'm filling things in sequentially, or filling things in based on the number, right? Like 1 will go in position 1, 2 in position 2, 3 in position 3. That means it's sort of by nature already sorted for me, right? So if I want to find the largest of something, I can start at the end of my array and just go all the way down and still get the same condition. That will necessarily give me the largest out of all of them. So in that way, we don't have to, like I said, you might be tempted to, like, I don't know, anytime you find a new, like let's say we found 1, 2, 3, right? You might find, oh, 1 is equal to 1, so let me push it in some array because that's a candidate. And 2 appears twice, so I'll put 2 and 2, and then 3, you know, these are all candidates, and then maybe I'm going to return the max of this array at the end. You know, you might think to like create this array, and then at the end, I might say, oh, return, you know, math.max of the candidates that I have so far, right? But this is going to incur more space because of the creation of this array here, and it's also going to incur more time because math.max is it's a linear time operation. So two very important things I want you all to take away. I'm very, very happy about this question. Phenomenal question. Nice. Cool. All right, let's get to the next one. Oh, well, that's it. Now we're going to have 100 questions now on my list since we did 2. I'm very happy with the questions we've done on this stream. So let's see. Hopefully we continue on this streak. All right, looks like it could maybe be good. The Tribonacci sequence is defined as follows. Given n, return the value of n. N equals 4, 4. So T3, 0 plus 1 plus 1, 1 plus 1 plus 2. Wait, what? T4, T3. Oh, I see. Is this like Fibonacci, but without... I'm curious. Is this the same thing as Tn plus 3 is Tn plus 1 plus Tn plus 2? I mean, I feel like we can do the same as Fibonacci here. I wonder if we'll get time limit exceeded if we just try to go for something quick. So 0, 1, 1. So I think that if n is less than or equal to 1, we should be able to return 1. Now, can we just return Tribonacci of n plus Tribonacci of n minus 1 plus Tribonacci of n minus 2? Is that a thing? I just want to see if we even get the right answer before thinking about optimization. If n is less than or equal to 1, return 1. Why would that break? Did I not? Right? If n, return 1. Is this one of those like really dumb mistakes here? Oh, maximum call stack exceeded. Okay. For which case? 4? So already it didn't like that? For T of 3, T3, 0 plus 3, T4, trying to understand how this works. For T4, n plus 3, Tribonacci sequence Tn is defined as follows. T of 0 equals 0, T of 1 equals 1, T2 equals 1, and Tn plus 3. Given n, return the value of Tn. The answer is guaranteed to fit within a 32-bit integer. Tn plus 3. So T of 0 plus 3 is 3. Why not just do 1 plus 3? Oh, so it wants 1 and 2. 0 plus 1 plus 1 is 0. 1 plus 1 plus 2 is 4. I'm not sure I'm seeing like this piece right here. How are they? I mean, I know it literally says it here, but t of n plus 3? Given n, return the value of t of n. T of n plus t of n plus 1 plus t of n plus 2. Nth Tribonacci number. Tribonacci n plus Tribonacci n minus 1 plus Tribonacci n minus 2. If n is less than or equal to 1, return 1. I'm curious how that would... Oh, is it because, well, tn plus 1 plus tn plus 2. Should it be tn? Oh, wait a second though. n plus 2. I wonder if we can do... Are you returning sum of last 3 digits in Fibonacci? Is that the question? It's confusing. Yeah, no, it is confusing. I'm not sure if this is asking me to do like Fibonacci with 3 numbers or something else. It's weird. But let me think about this real quick here. Tn plus 3. Now, like, the n here, it represents this, right? Am I just like going crazy? Return the value of tn. Well, what is tn here? If I subtract tn and tn, right? So we'll do tn. I subtract it, so tn minus tn. Then here, can this be minus tn plus 3? But this is going to be a negative, right? Negative tn equals t, but like what is the tn plus 1 plus tn plus 2 minus tn plus 3? Given n, 0, t1, 1, t2. Like what is... plus 3 tn. Return the value of t4. So like if tn plus 3, is that saying that 7 equals 4 plus 5 plus 6? Is that what that means? Like if n is 4, are they telling me that this is essentially t of 7 equals t of 4, t of 5 plus t of 6? Is that how it is? So how do we get to 4 now? If I want to get to 4, I need to do t, like t of 4 would be equal to t of 1 plus t of 2 plus t of 3. And t of 3 is t of 0 plus t of 1 plus t of 2. Okay. Trying to figure this out. So if I'm given 4, I need to figure out minus 3, minus 2, minus 1. I think that might be it. Wait, let me see what that does. Okay. I feel like we're getting somewhere. But still, what does it want me to return? 4? Oh, and we're not supposed to actually, I see. We're not supposed to add all these up. We're supposed to figure out. Yeah. Okay, you know what it's time for? It's time for Excalidraw. This has helped us a lot in the past, and I'm sure it's going to help us this time. I think what I need to do here is draw some circles. Circles always help. So what's the answer that I have so far? We're trying to get t of 4. That's going to be, it's going to call like 3 things. So this already is going to be 2 to the power of 3, right? Because every single time there's 3 branches. This is going to be 1, 2, 3. This one will just return 1, but then this one is also going to call 3. that we'll call what? -1, 0, and 1. And then I'm gonna zoom out here. Sorry if this is like kind of small. I'm just trying to save on space. This will also call what? 0, 1, and 2. I'm gonna draw some arrows here to make it all a little bit easier to read. I'm not trying to find optimizations right now. I'm trying to understand the question a little bit more clearly. This will call 0, 1, and 2. So we just want 4, right? 0, 1, 2. They want 1 plus 1 plus 2. It's just Fibonacci, but instead of starting with 2 numbers, you start with 3. Right? That's not what we did here. Maybe I'm just Tribonacci n minus 1. Return Tribonacci of n minus 3. But the fourth one, this is going to be 1. This will be negative. Where's the 1 coming from here? 0 plus 1 plus negative 1. This is going to call minus 3 minus 2. This should be plus 2. Oh, wait, this should be n. This should be n. Let's see if that does anything. Aw. Or do I have to be even more... Do I have to be more exact? It'd be like if n is equal to 0, return 0. If n is equal to 1, return 1. Return this. Call stack again. Maximum call stack exceeded. Or if it's less than or equal to 0, maybe... Oh, I think we made some progress. Is the problem in the base case? Yeah. So two things I did, and I tend to do that a lot. Like, I just thought if it's less, but then that wouldn't work, right? Like the first thing that something was wrong was this, where I had if it's less than or equal to 1, return n. But as we saw from our drawing here, n can sometimes be -1, and we don't want that. I think we need to be a little more precise, and we need to say for very specific cases, if it's less than or equal to 0, we just return 0, and if it's 1, we return 1, else we return this. And it looks like I got at least the first test case right. However, there's a very high likelihood that this question will TLE, time limit exceeded, because they probably want us to use some form of memoization. Let's try it out. If that's the case, that's good, because it means that questions are becoming harder and they want us to think more out of the box. Okay, so time limit exceeded. That's exactly what I thought would happen. So let's do something. The classic memoization is we pass in sort of like a cache, right? And we can always say these base cases, that's fine. Else here, we should say that if memo of n is not equal to undefined, right, then we can just return memo of n. And then here, we'll cache our result in memo of n. And finally, we'll return memo of n. So let's run our test cases again. Okay, submit. So if this doesn't work, I'm gonna be like very curious. Oh, wait. I know why. I know why it's not gonna work. I didn't pass in my cache. Let's see, the last time this was 455 milliseconds. Let's run this. Test cases. 94. Look at that nice drop off. Is that still not gonna run? gotta be something we're not doing right here. NC. Okay, not equal to undefined. Return 0, return 1. If memo of n is not equal to undefined. Oh, wait a second. I think we can return memo of n here. Right? If it's not undefined, we should use that result. There you go. Let's go. That makes me happy. So what do we do here, guys? Like, I think we should draw out something here. So what we did is like, but without using memo, if we look at this, right, it's the same reason why Fibonacci is 2 to the power of n. Because for every level, I guess n is the level, every level it's branching out by 2. Here it's branching out by 3. So you're increasing like cubically, I guess, if that's even the way to say it, like 2 to the power of 3, right? 2 to the power of 3, or 2 to the n. Oh, maybe it's 3 to the n actually. Oh, nice. That one's a very good question. 2 sum 2 input array is sorted. Very good. We actually haven't gotten to 2 sum at all, which is crazy, but I'm very excited to get to that. That one is like, if there's one question you can do on LeetCode, like let's say you had an interview tomorrow and I can suggest a single question to do on LeetCode, it would probably be 2 sum. So let's look at something. Fibonacci time complexity. That's 2 to the power of n, right? I just want to see. Okay, yeah, 2 to the power n instead of O log n. Large difference. Consider size of the recursion tree as a function of the input size n. The number of leaves, n, is a binary tree is equal to the number of non-leaf nodes. I want to see like a better number. Let's denote n. It means that Tn is at least. This in turn means that Tn, direct formula, some constant, 2 to the power of n. For every single call, we're going to be making 2 more recursive calls. Here, for every call, we're going to be making 3 recursive calls. So this would be 3 to the power of n. Excuse me. So with, and like, why does memoization help, right? Because if you look at, like, I hope this has a good answer here. We have 1 and then we have 2, but these are all base cases, so I don't know if it's like, it might not help a lot. Oh, actually, okay, here, for example. Like, I'm going to have to make this very tiny, but I hope you guys can still see the 2. Oh, no, wait, I can actually do this instead. Right, so imagine we get to like this number 2. We've already solved this 2. We already have all the numbers, but then we get to this 2. Without memoization, we would go and branch off 3 more times and do the same thing, right? It would be -1, 0, and 2. 1, my bad. Right, it'd be the same thing. But because of memoization, because we have that cache, once we already solve for 2, right, we save it into our cache. So the next time we get to 2, we don't have to calculate all these again. We just return this since it's already in our cache. And I think, does that actually bring it down to be linear? Fibonacci with memoization time complexity. Is it linear? Assuming the memoization was done correctly, the number of operations will be the number of numbers generated. So it'll still be O of n. With memoization, O of n. Yep. So in this case, we did the same thing. We took it, and this is even a more drastic improvement, right? I mean, talk about performance. We went from a 3 to the power of n solution, right, all the way down to a linear solution. So I mean, that's probably why, and I appreciate the when you said wow, you know, it's like 99.66. Yeah, we've had 100% on the streams before, but yeah, that's very nice too, especially for a question like this. And yeah, it wasn't until I actually wrote it down. Again, I need to do that more often, but until I wrote it down did I not understand it. So we're on a roll. Rashawn says, gotcha. So it's like it remembers what you previously used. Exactly. It's just like a cache. That's how I see it. I mean, think about caching. I don't know if you have any experience with like just HTTP, but think about caching in HTTP or caching using other services like Memcached or Redis. You know, any of those caching services or any sort of caching layer where you don't have to go back to the origin, you don't have to do some calculation again, it saves you time. And this is exactly an example of that. So very cool. Awesome. Yeah, thanks a lot. Great question. All right, we're on a roll, not only in the sense of like we're going through these questions, but these have been 3 amazing questions. Super, super high quality questions. So let's keep going. Add digits. Okay, so given an integer num, repeatedly add all its digits until the result has only 1 digit and return it. Okay. 3, 8 becomes 11, 2. Okay, well this is, oh, can you do it without any loop or recursion and O of 1 runtime? Has only 1 digit. Is there this? I mean, I would do it like this in the sense that I would do a loop for this, but you know, this probably just has like a very simple math solution. Could you do it without any loop or recursion? O of n runtime, constant runtime. I mean, the output will always be from 0 through 9, right? Because only 0 through 9 has 1 digit. So how do we figure out if it's ever any one of those? Could we just like if it's 3 plus 8, is it just the difference of 3 plus 8 minus 2? If I did like 49, would that be 4? Would the answer of 49 be 4? I'm curious. 49 and 0. Yeah, that's what I think. Yeah, 240 exactly. Now, the way to do this is how can we, without doing the loop, how can we add, this goes up to how many? 0 through num of 2 to the power of 31. How can I now add up all the digits though? Return 1 plus num minus 1. Oh, that's the answer? Wait. Yo. User submitted answer. Whew. Wait, how does that work though? 1 plus num minus 1 modulo 9. I am confused about this. 1 plus, because is this some other trick I don't know about? How you can add all the digits of a number? 1 plus, like num minus 1 is 37. Wait. Is this a trick to add up all the digits in a number? I'm very curious about this. I guess it's not really this, right? You're telling me, wait. Means num, no, I understand that. Num modulo 9 plus 1. Oh, is this just because of the, okay, so maybe this is not, yeah, that was quick, man. That was good. I certainly don't really understand that one. Given an integer number, repeatedly add all its digits until the result only has 1 digit and return it. 11. How do we know it's always going to be 1 through 9? Is that because I guess it's just the range. How many times does 9 go into it? And just the remainder of that. This will return the last digit of the number if it is not 0. Oh. Oh, and that's really all we want, right? That makes sense. Man, that was... I really wish, like, there's got to be... I wish there was, like... I need to look into a way to, like, give people applause or something. Like, bring up a GIF on the stream when cool things happen. That's awesome. That was a cool question. I'm just happy that I was able to figure out the, you know, it could only be 1 through 9, because it sounds easy, but that could certainly be a gotcha. So I'm happy about that, but that's super cool you provided this. I don't think I'll add this to the list just because the ratio is so bad, and I think this is mostly a trick question or a math question, but still very cool. Yeah, thanks a lot for that, Rashawn. All right, let's get to the next one. So calculate amount in paid taxes. All right, are we coming into bad territory now? The first time that this is sort of in the other direction. Let's see, we're given a 0 indexed 2D integer array brackets where brackets I equals upper and percent. It means that the ith tax bracket has an upper bound of upper and is taxed at a rate of percent. The brackets are sorted by upper bound. Okay, so all these 3, 7, 12. Oh, okay, I see. You're given an integer income representing the amount of money you earned. Return the amount of money that you have to pay in taxes, 10. Based on your income, you have $3 in the first tax bracket, $4 in the second tax bracket, and $3. Oh wait, this is upper bound and percent. Okay, so we have in here, let's see. So like for our number, income, right? So we see like I can go up to 3. So just put 3 because I have 3 available. Let's see, go pick, I guess we can, should we pick the min? Yeah, pick the min of income or upper bound. I think that's what we can do. Because here I can say 3 or 10. I'm going to pick 3. And I'll subtract 3 here to get 7. I can pick 7. And I'll subtract 0. And then here will just be 0, right? 2.65. And $3 in the third tax bracket? Wait, why is it 4 if the upper bound is 7? Oh, it doesn't necessarily have to be $4. 3, 4, 7, and 3. 10 and $3. You're given an integer. Oh, wait a second. The first upper dollars earned are taxed at a rate of percent. The next upper 1 minus upper dollars earned. Oh, the next 4. And the next, so is it just 3 is 7? This one's weird. Yeah, this one just seems terrible. I don't even think it's like necessarily hard. I just don't think it's a fun question. I'm just trying to think of like, it's just hard to like put into code. Based on your income, you have $3 in the first tax bracket. So does that just mean, okay, upper bound of upper, the brackets are sorted. Does that just mean that's like anything up to this should be taxed at 50%, right? So I thought it would be like, okay, a third of my 10 was taxed at 50. So now with the remaining 7, shouldn't all of them just be taxed at 7? $3 in the third tax bracket. The 3 is the thing I'm confused about. Where does the 3 come from? And why do we only pick 4 here? 3, 7, and 12. Does anyone know why? Let me see. Based on your income, you have $1 in the first tax bracket and $1 in the second tax bracket. Because I have no money left. So I thought $3 in the first would make it so now my income, should that not reduce my income? I guess I still have, I thought it would mean like, okay, I have $70 left, let's say. And those remaining $70 would be taxed at 10. But let me think about this. I should know how this stuff works, right? I mean, I pay tax. And I know this is very similar to how it is today. Like everything up until a certain amount is taxed at this amount, plus everything from, oh, wait a second, 4, 5, 6, 7. Is that inclusive? Oh, I think I see. This is saying from 0 to 3. And then we're going to go from 4 through 7. And then from 8 to 12. But I can only pick 3 because I have 8, 9, 10. I think that's what it means. Yeah, so what we could do, yeah, okay, I understand now, but it's just like putting it into code. That's like a little bit weird. You can almost say like, okay, for the first one, just do the 3 automatically. And then for the second one, go from the previous upper bound plus 1 to the current upper bound. That's however much you'll subtract, or that's however much will be taxed at 10%. And then if the number is greater, okay, it's going to be a little bit weird, but let's see. For const bracket, and what I'm going to do here, I'm going to say is what? This is upper bound and percent. So let's do upper and percent of brackets. Let's do something. Let's do let previous upper bound equals 0. I know I need to do something like if upper is greater than income. I'm going to save this one for later, but I think what I can do now, let's do tax equals 0. All right, so we get to this first one. We get to this first one here. And what do I want to do? I want to subtract previous upper bound is 0. Oh, let's say like const taxable is equal to upper minus previous upper bound. We can say tax plus or equals taxable times, and this is 25%. Right, so we should divide by 0.5, right? We should divide by this. Oh man, math. Math, guys, math. Yeah, okay, 0.5. So I think here we should do taxable plus or equals taxable times. Let's see, math.floor, no wait. Const normalized percent equals math.floor of percent divided by 100. Yeah, it's weird. Normalized percent. Tax, we can do taxable times normalized percent. Okay, and then we can set previous upper bound equals to upper. So let's think about this. Like, if we're going through all these, I'm going to write this again. I feel like there's an edge case I'm missing here, of course, but I'm fine with that. we'll figure that out. So we get to like this first one here. So if upper 3 is greater than income, which it's not, so we go here. Taxable is now upper, which is 3 minus 0, which is, so that's 3, right? Now here we can say normalized percent is percent divided by 100, and we can say tax is equal to taxable, which is 3 times this normalized percent. We add that to tax, and now we set previous upper bound here to 3, and tax becomes what, 1.5? Let me go to the next one. Okay, cool. So if 7 is greater than income, no it's not. We go const taxable is equal to upper, which is 7 minus 3, that's 4, right? 4 times 10%, however much that is. Obviously I'm not really very good at this. And then we get whatever answer that is, and now we can set previous upper bound to 7. We add some number in here. I don't know, I'll make it 2.5 for now, whatever it is. And now when we get here, this is sort of like the special case, because I don't want to do, like, if upper is greater than income, which it is here, then taxable here should be income minus previous upper bound. So I think what I can do here is say taxable. That way I can declare it once here, sort of take advantage of just doing some refactoring here. And then I think really that will be that might be the only difference, and then we just do this. We can even say this. Income minus previous upper bound, or upper minus previous upper bound. Remove this here. Normalized percent. Let me see if we can get, instead of previous upper bound, maybe we can just say previous upper, just to shorten it up a little bit. Here we can say, maybe instead of normalized percent, I'll just go ahead and stick that in there. I'm just trying to refactor this a little bit. Tax, let's say this is 0, previous upper is 0, and then at the end we return. Let's see what happens here for this one though, right? This might change everything. So we come to I here. 1 is not greater than 2. So we can do taxable, upper greater than income, no. So we'll say 1 minus 0. We'll do the tax thing, previous equals upper, then we get to here. So now this is greater. So what do we do here? We do like 2 minus 1. And that's it. I think we can only do that once, and then we don't do the rest. If upper is greater than income, we can still tax it, but then I think we should just say if upper is greater than income, we break. And then here we can return the tax. I think that might be okay, but let's see. A weird question indeed. 0, 0, 0, 0. Beautiful. That's all right. Let's see where we could have gone wrong. Brackets upper percent. If upper 3 is greater than income. So we do upper, which is 3, minus previous upper 0. Tax plus or equals 3 times math.floor of percent divided by 100, right? Just make sure. I think we did that before already, right? 3 times 0.5, yeah, 1.5, that's fine. Tax plus or equals, oh wait, did I return tax? Okay, yeah. That's weird how it's 0. Did we not, you know what, we probably didn't get to if upper is greater than income. That's so strange. How did we get 0 here? I would have at least expected one thing. Taxable times. Not even const upper percent of brackets. Okay. If upper is greater than income, if 3 is greater than 10, which it's not, so we do 3 minus 0. So taxable is 3. 3 times math.floor of percent. Oh, we shouldn't do math.floor here, right? Okay, 2.65. Let's get to the next one. Okay, I mean, hey, two test cases, 3 test cases are good. Are we gonna get it, guys? Are we gonna get it? Let's see. Nice. Cool. Yeah, I think, like, I guess this question's bad. I don't know. I mean, it's not terrible. There's definitely worse questions than we've done, but this could be kind of tricky. I think people don't like it because it's like a wall of text and maybe it's not explained very well, but I'm pretty happy with it. I mean, it's constant space complexity and it's a linear time algorithm. Like, I'm curious how this is so low. No title. Okay, sure. I mean, yeah, previous is 0. Income, yeah, similar. No title. I'm happy with this. 77.11. I feel pretty good about it. Even though maybe it's not the best thing, I like it. So let's see. We're at 204. Let's see how many questions we did today. 209. 5 questions. Another 5. I mean, we're getting back to doing like 5 through 7 like we did early on in this whole journey. It either means that questions are just easy, we're getting lucky, or ideally it's because we're getting better. And I think it's the latter. So we did how many? We did 1, 2, 3, 4, 5 questions. And honestly, I think like majority element, find lucky, and Nth Tribonacci were amazing. I'd actually say add digits is worse than calculate amount paid in taxes. I might add this one to my list. I kind of like it. I don't know. But definitely these 3. Ignore the premium one, but definitely these 3. That means that by the end of today, we'll have 4 new ones for a total of 102 questions. Pretty amazing stuff. So to everyone that's watching, thank you all so much for watching. If you like doing LeetCode, if you like watching someone like me try to develop an optimized algorithm and talk about my thoughts out loud, then definitely make sure to subscribe to my YouTube channel. You can find my YouTube channel let's actually go to it if some of you are not aware. You can find it here, LeetCode Live, daily LeetCode streams. You can find all my streams here. You can see all the ones that we've done in the past. Make sure to ring that notification bell to keep up with all my streams as they come out. And then of course, if you're on Twitch, make sure to follow me on Twitch. That way you can always know when my streams are happening. Tell your friends, tell your family, tell your colleagues. We're out here making things happen. We've now passed the 200 question mark, and that means something. So if you've been around with me since day 0, give yourself a pat on the back. We're making a lot of progress. So you guys have a great rest of your Thursday. Tomorrow's Friday. Thank God. That's amazing. And we'll see you all then. So have a great evening or morning. I'll see you all next time, and happy coding.